Hi, everybody. So my name is Caroline. I work on AI frameworks at Microsoft, and today I'm going to be introducing ONNX Runtime Training on Web. So today I'm going to be giving an introduction. Sorry, what was that? Is this? Okay, I think I was just holding it too far. But okay, so for today's presentation, I'm going to give an introduction to ONNX Runtime and a quick overview of on-device training. I'll talk a little bit about ONNX Runtime Training on web usage, and we'll finish up with a quick demo. So I'm sure most of you already know what ONNX Runtime is, but for those of you who are unaware, ONNX Runtime is a high-performance runtime for ONNX models. It's available in a whole suite of different languages, including Python, C#, Java, etc. It's cross-platform and it's extensible to plugin optimizers and hardware accelerators. Finally, we offer both inference and training. Our inference engine is available across cloud, desktop, edge, web, and mobile, and it's lightweight and efficient. We also offer two types of training. The first is on-device training, which is what our presentation will focus on. And we also offer large model training. So this would be server-side training for compute-intensive models, usually on some kind of hardware acceleration. So on-device training refers to training machine learning models on edge devices. So think things like your phone, laptop, tablet, etc. Now, why would you want to do on-device training? Well, a lot of data exists on user devices, and these are generally resource-constrained devices, so they don't have a discrete GPU, and they might not have a lot of compute power. We want to maintain the privacy of user data and also create portable solutions that are available across a wide variety of devices. So our solution was on-device training with ONNX Runtime. It's a memory and performance efficient trainer that allows training a model on the device, and we target personalization and federated learning scenarios. These scenarios are privacy aware, so they allow users to train a machine learning model without compromising user privacy, and they're easy to scale across multiple platform targets. So they're available with simple APIs across C, C++, Python, and more. We allow the same solution to run across cloud, desktop, edge, and mobile, and we make it easy to move from training to optimized inference using the same packages. With that background on on-device training, I want to talk about the existing solutions in the on-device space. So on the right, you have Executorch, which is PyTorch's on-device inference engine, but there is no support for training yet. And then along the left, we have TensorFlow Lite and TensorFlow JS, which are two distinct solutions. TensorFlow Lite is TensorFlow's answer to on-device training and inference. It exports to a model format that's called TensorFlow Lite, so you're restricted to the TensorFlow ecosystem. TensorFlow JS enables training and inferencing in the browser, but they only support exporting to JSON files, so you're even more narrowly restricted to the TensorFlow JS ecosystem. Neither of these solutions use or benefit from the ONNX model format or the ONNX ecosystem. I want to pivot back to the two scenarios that we target. So on the left, we have personalization. In this scenario, a model would be fine-tuned on user data, and then it would be immediately available for inference on the user device. So in this scenario, neither the user data nor the fine-tuned model leaves the device. So in this way, you can create things like personalized algorithms and models for users without compromising user privacy. The second scenario, federated learning, is a machine learning technique that enables you to train a global or central model using multiple edge devices. And the way that it does this is that there is like a federated learning agent or framework on a central server that is responsible for orchestrating multiple edge devices. So these edge devices would each receive their own copy of the model, fine-tune them, and then send just the model parameters back to the central server. So the central server receives multiple copies of model parameters, and the federated learning agent aggregates these parameters and updates the central model. So in this way, you can train a global model on user data without necessarily sending that user data to the central server. ONNX Runtime on-device training has an existing flow that I want to talk about. So this can be broken down into offline steps and on-device steps. Offline steps are considered offline because they happen off of the device with the user data. So think like a central server. And these steps would generally be performed by a data scientist. First, you would export to ONNX. And then once you have the ONNX model, we provide an API to generate training artifacts. You need 4 training artifacts for on-device training. So the first is a checkpoint, which contains all of the model parameters. And then a training model, which includes the gradient operators and a loss node. An eval model, which looks very similar to the inference model, except it has a loss node added as well. And then an optimizer model, which includes the strategy for updating the model weights. Once you have the training artifacts, you would move both the training artifacts and the training-enabled mobile package to the edge device. And then we can proceed with the on-device steps, which would generally be implemented by an app developer. So you would fine-tune the model on the device, and then we offer 3 post-training options. The first is saving a checkpoint, and this would be done in a scenario where you want to pause training and then resume it later. We also offer the ability to export for inference, which would be done in the case where the model is at a point where it's ready for inferencing. And finally, we allow users to extract weights in memory. In other words, provide the model parameters as a buffer, which will be used in the federated learning scenario. With that background, we can finally jump into ONNX Runtime Training on web, which enables on-device training in the browser. So this is a capability that's built into the ONNX Runtime Web NPM package. And for those who are unfamiliar, NPM is a package manager for Node.js projects. And it's been available with ONNX Runtime since 1.17 release. It's a lightweight and optimized solution for browsers, and it supports the CPU execution provider, which means that it's available on every browser. We target the federated learning scenario, and that's because web has a limitation where it doesn't provide a robust file system API, limiting our post-training options to the federated learning scenario. This diagram goes into some of the technical details of federated learning with ONNX Runtime. Just to give a high-level overview, so the server would send the model parameters to the web app, and then along the right side of the diagram, the user data would move through the different layers of the app and the package. The training would happen, and then along the left side of the diagram, the model outputs and parameters would move back up through the different layers of the app, and then the web app would send just the model parameters to the server where the aggregation step is performed. And finally, some notes about usage. So first, you need to import the package. ONNX Runtime Web uses WebAssembly binaries, and WebAssembly is an optimized, efficient binary format for the browser. The thing about WebAssembly binaries is that they have to be served to the browser to be used. JavaScript projects generally dynamically serve files, which can make correctly serving the binaries a little bit difficult. So you need to import the package one of 2 ways. The first is like through an HTML script tag, which hosts the package in a third-party client, and it ensures that the binary is correctly imported to the browser. The second is through a web bundler, which is a technology that compresses files served to the browser, and also allows a lot more fine-grained control around dependencies. If you use a web bundler, it takes a little bit of manual configuration to serve the WebAssembly binaries, but we have detailed examples for all of these import methods available on ONNX Runtime inference examples. And then we have the training flow. So you would take the aforementioned 4 training artifacts and load them into a training session, which is an object that orchestrates the training model, its weights, and updating them. You would run train step on inputs, and then you would run optimizer steps to update the model weights. And then optionally, you can run eval step on validation data. Finally, you have the post-training option of exporting model parameters. And then we can get into our quick demo. So this demo showcases the MNIST dataset and task, which is a handwriting recognition task. At the top, we have some background and some training options, such as the number of epochs and the batch size. Oh, let me reload the page. Okay, I'm just gonna go ahead and hit train. And very soon you'll be able to see the training loss decrease in real time, as well as the test accuracy, which is measured after every epoch. Along the bottom, you can see the real-time predictions from the model for the digits. I think it's happening a little bit slowly because I'm not sure why, actually. It usually takes like 30 seconds. Okay, well, while this is running, I also want to mention that while web browsers don't have any hard limits for memory usage, it's entirely dependent on the compute power of the host machine. The WebAssembly binary format that we have has a 2 GB memory limit, so that's just something to keep in mind. I also have some metrics listed at the top, and I just want to mention that measuring performance and memory usage on the web can be complicated. Things like the number of extensions and the screen resolution of your user's machine can drastically impact the memory usage of your web app. But these numbers are more meant to show that training machine learning model in the browser with ONNX Runtime Training doesn't have to be compute or memory intensive. Okay, I mean, it's still training, but it pretty much just looks like this. Okay, back to the presentation. Here we have some links and resources for getting started. And that's about it.
Hi. How do you actually test? Is it really transitioning the training session into an inference session, or is it keeping the training session alive but not running the optimizer?
What do you mean by test?
In the sample that the demo you just showed,
Oh, the test digits.
the test set.
Yeah, that's basically the result of running the eval step.
Yeah, but how do you realize the eval step? Is it disabling the optimizer, or is it basically having an inference session as you would usually have with ONNX Runtime?
The training session provides you with the option to run the eval step. So one of the training artifacts that you can load is the eval model, which looks really similar to the inference version of the model. It just also has the loss node attached and then sometimes a labels node, so you can get statistics like loss.
Okay,
Yeah.
cool. Thanks.